All right, so let's see where we've been and let's see where we're going. We know that f prime of x, we have this limit definition for a derivative. The limit as h approaches 0 of x plus h minus f of x over h. And you should feel very comfortable with this limit definition of a derivative at this point in time. If we relate this to a graph, we know that if x equals some point a, then f prime of a represents the slope of the tangent line at that point, specifically a f of a. Now, the way we have been showing this is we've been using f prime of x. That's been our derivative notation. But as it turns out, there's another notation for a derivative because there were two mathematicians that get credit for discovering calculus. One of them is Isaac Newton, and the other one is Leibniz. And Leibniz had his own notation, which was df dx, or he would say dy dx, which is the derivative of f with respect to x, or the derivative of y with respect to x. So you're going to start seeing both of these notations. We use them interchangeably throughout calculus. Either way, a derivative is going to be the units of x divided by the units of x. So if it's a position function, we're talking about miles per hour or meters per second or something like this. So let's consider this idea. P of t is the population of Vernon Hills as a function of time. P is measured in thousands, t is measured in years. We're going to let the arbitrary zero be 2010. If I say p prime of 2 equals 21.37, how would you interpret that statement? What does that statement mean? How would you explain it to someone who didn't know anything about derivatives? Well, it turns out that p prime of 2 equals 21.37 would mean that the instantaneous rate of change at 2 years after 2010, so in the year 2012, is 21,370. So we would expect during the year 2012 that the population of Vernon Hills were to grow by 21,000 people, 21,370 people. Okay, so here's an idea. Let's say that we have a function f of x where we have three values. F of 1 equals 2.5, f of 2 equals 3.25, and f of 3 equals 3.625. Our job is to estimate f prime of 2. This doesn't seem like too tricky of a problem at first until you realize you don't have much information about this function at all. I don't have a function. I don't have an equation. I don't have a graph of the function. All I'm given are three function values, and now I got to figure out the instantaneous rate of change at f prime of 2. I should say estimate at f prime of 2. So since we're trying to find f prime of 2 and I know f of 1 and f of 3, we could let h represent a negative 1, which would be the average rate of change from 1 to 2, or we can let h represent a positive 1, which would be the average rate of change from 2 to 3. So let me back up for a second. If we can't use the limit definition because we don't have a function. So if I have f of 2 plus h, I have nothing to plug that into. So that's a problem. We can't use smaller and smaller values of h on the calculator. We can't use a table of values because, again, I don't have a function to put in my calculator. So here's where we say we can let h equal negative 1 or we can let h equal positive 1 simply because I know f of 1 and I know f of 3. So that's an h distance of negative 1 or positive 1. Okay, so we can say f prime of 2. If h is equal to negative 1, we can say f prime of 2 is approximately the average rate of change from 1 to 2. All right, so that's going to be f of 1 minus f of 2 over 1 minus 2. That equals 0.75. If I were to let h equal positive 1, then I'd be finding the slope of the secant line between 2 and 3. So f of 3 minus f of 2 over 3 minus 2, that's 0.375. Now these aren't really close to one another. Yes, they're both less than 1, but they're still quite a ways away from each other. So what we can do is we can take the average of these two values. Since I have these two values, take the average, and I get the slope f prime of 2 to be approximately 0.5625. Okay, Now, let's take a look at what we just did there. So this graphic is good, but it's not great. Here's 2 right here on the x-axis. All right. Now, f prime of 2 is going to be the slope of this green line right here, which we don't know. We have no idea because we don't know what this function is. We're only given f of 1 and we're given f of 3. So when we found the slope of the secant line between 1 and 2, we found this gray line right here that I'm tracing with my highlighter. And when we found the slope of the secant line between 2 and 3, we found this gray line right here. And we can see that those slopes are nowhere close to being the same. But if we take the average of them, the average of those 2 slopes ends up being this green value right here. Now, perhaps an easier way to do this, don't get mad because I'm going to show you an easier way to do this now, is we could simply find the slope of the secant line between 1 and 3. Right? So this red line right here represents the slope of the secant line between 1 and 3, which is darn near the same. It's not exactly the same, but it's pretty darn close to being the slope of the secant line or the slope of the tangent line at 2. So as long as we're equidistant away from 2, in this case a value of 1 to the left and a value of 1 to the right, we can just calculate that average rate of change between 1 and 3. This is what we call in the biz a central difference approximation. Let me go back for a second. As long as you understand how to find the slope of this red line, and as long as you understand that we have to be equidistant away from 2, in this case it's 1 unit to the left and 1 unit to the right, you're fine. You don't even need to look at the next slide because the next slide is going to give you a formula, but you don't need a formula for this. The formula actually gets in the way of the concept. So if you understand everything up until this point, don't get too hung up on this formula. F prime of A is going to be approximately f of A plus h minus f of A minus h over 2h. It's basically taking the slope of the secant line for h distance to the right of A and h units to the left of A. All right, so it measures the slope of the secant line between those 2 points. And that's where we will stop.